Hello guys, so this time I want to talk to you about signals. This was our lecture from December 1st and 2nd, I believe. Okay, so the signals come in two flavors, analog and digital, but before we talk about those flavors, we need to talk about what signals are. And a signal is information. So my definition is signal is a piece of information. Now, it's also a code, guys. So right now, as you're watching this video, I'm talking to you in code. That's because I'm talking to you in English, and you know this code, and you can decode it. If I were to talk to you in a language you don't know, it would just sound like random collections of sounds. You will not be able to understand and decode that signal. So signal by itself is really, it's also a code. You should be able to read that signal. So in our world, signals comes in two varieties. You can have analog and you can have digital. And the best way to understand the difference between the two is to actually compare the analog and digital clock. So here's an example of analog and digital clock, and you can see that they're both showing exactly the same time, 3:45. So the main difference is really when you look at the time that you can show. So they can both easily show 3:45. But what about 3:45 and 3/4 of a second? The, the digital clock cannot do that. And the analog clock very much can. When you look at the analog clock, the minute hand never actually stops moving, even while the minute is going on. At this point, the minute hand have just reached 3:45. But as soon as it reaches that number, it keeps on moving until it reaches 3:46. So basically, if you can build a big enough analog clock, you can have a small fraction as you want of a second be displayed on it. With the digital clock, no, you would need another space and then another space and another space and so on. And that would require rewiring the entire clock. So one thing that you would like that you can take away from this is that in analog clock, time keeps on moving. And in digital clock, at exactly 3:45, the time freezes and stops until it's time to show 3:46, and so on. So every single second, it acquires the value, and then it freezes for that second at that value, and then it keeps on moving. All right. Another way, when I'm thinking about the signals, I also often think about audio signals. And one way to think about audio signals is to think about the graph of an audio signal. And I'm going to make a graph of a couple of audio signals. One's going to be analog and one's going to be digital. And we're going to compare the two. So when you think about an audio signal, there could be a lot of things that you can chart. And I'm just going to plainly chart loudness versus time. So here's my signal. Here's my signal, and let me put down my axis. So this is time, and this axis is time, and that axis is going to be loudness. Okay, there we go. So notice that this signal is continuous. So maybe you have a track and it starts at 0, as in there is no sound, then it gradually gets more and more loud, then it dips a little bit, and then it gets even more loud, and then it kind of dies out really quickly. And the nice thing about this signal, as in, any piece of music, you can't really distinguish one note from the other. It just keeps flowing and flowing, and it's really, really nice. So now let's take a look. How would that look if this was a digital signal? So a digital signal, just like the analog clock, let's say every second or so, we acquire a value. So the first value we're going to get is 0. And we're going to keep it 0 for a while. And then we're going to get our next value, and that's going to be right here. And we'll keep that value for that precise time interval. And then it's time to get another value right here. And then it's time to get another value right here. And then it's time to get another value, and it's right here. And another value right here. And then another value right here. And so on. So if I were to redraw this on a separate graph, I would have this weird thing. So let's see if I can replicate this. So I had this one, then 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 I had the one over here, then I had the one over here, and then I had the one over here. This looks nothing like that graph. So what happened? I chose a bunch of values, and I'm only playing those values. And all those shades of in between are lost. Remember how I said that music is, you can't really tell one note from the other? Well, this is not it. This is like throwing away most of your music and just playing a couple of notes from it. So this is digital. So why then we actually play music in a digital format all the time? That's what we get when you listen to music on the phone. My voice, as I'm speaking right now, and it's getting recorded, it is going to get digitized, and you're going to listen to it through a computer, and that's going to be in a digital format. So how come it doesn't sound so horrible? Well, one of the reasons it doesn't sound so bad is that it all comes down to a question of a sampling rate. And sampling rate is how often you get those values. Now, if you have a sampling rate of 1 value per second, then of course it's not going to sound good at all. But if you're going to have a sampling rate that's much higher, then after a certain point you cannot even tell which one's digital and which one's analog. One thing you might think about is that little book, a flip book that you can draw, that you can do, you draw on the edge of a notebook a stick figure, and you make it run by flipping through the pages, because you make slight changes to its legs. This is the same idea when all those values, when you have enough of them acquired that they're so close to each other that your ear cannot really distinguish the difference, then it sounds very analog to you. Okay, so it all comes down to something called sampling rate. And sampling rate is number of values per second. And guys, you actually know all about sampling rates, because if you ever download music from internet, maybe you're doing it from iTunes or some other site when you can pay for the song and download it on your phone, and you have a choice of getting a song that is 64 kilobits per second, or you can have 256 kilobits per second. I mean, which one are you going to choose if you're gonna have a higher, if you want to have better sound quality? Of course, you're going to choose the higher number. But if you don't have enough space on your phone, then maybe you want to choose the 64, because if you have less values, like I have over here, then you don't have to use as much memory. So that's really the breakdown of what sampling rate is. Alright, so this class is going to be mostly about digital signals, and we actually not even going to talk about signals that complicated. The main thing that I want you to take away from these signals is that this signal, the analog signal, is continuous. And it's also smooth, there are no sharp angles, there are no, little cusps. None of that is present in that graph. And digital signal is discrete. And discrete means it's disjointed like this. It's like you hop on little ladder like this. Okay? And that is all about signals.